Welcome to Hyperfixation Investigations, the podcast where two neurospicy best friends take time each Saturday to infodump their research deep dive of the week.
Lovingly produced and copyrighted by Wolf and Stag Productions.
Today's fun fact is there are 48 tons of space debris that fall to Earth every day. Luckily for us, most of it burns up in our atmosphere.
Good morning, I'm Josh, and I'll be captaining this week's episode, Shooting Stars.
Good evening, I'm Kara, and I'm just along for the ride. For those of you joining us for the first time, here's how things work. Josh will be leading us through a mini lecture on the topic, and we'll discuss it throughout the episode.
Expect tangents throughout. We switch off duties each week, so next week expect Kara to helm the episode.
Now to our regularly scheduled program. Josh, what have you been hyperfixating on this week?
Well, Kara, I've been thinking a lot recently about meteor showers and shooting stars.
Ooh.
And in fact, this episode is partly in honor of a meteor shower that is currently ongoing.
Fun.
Yes. Now, before we actually get into talking about that meteor shower, my plan today is to first talk about the various types of celestial bodies that occasionally impact the Earth or are otherwise involved with shooting stars. Mm-hmm. Differences between them and how they relate to shooting stars. We will eventually get back around to discussing the Quadrantids meteor shower that is currently active.
All right.
Yes. So there are really three main types of celestial objects that I'm going to be touching on today. Mm-hmm. Asteroids, comets, and meteoroids. And yes, I'm going to get into the whole meteor versus meteoroid versus meteorite thing in like just a moment.
Okay, cool.
Technically, all of these things are now classified as small solar system bodies, and that definition was actually part of the same document that defined Pluto as a dwarf planet.
Rude!
I mean, yes, but...
Hades/Pluto always gets a fucking bad rap, and it's not fair.
No, but I'm literally just going to go to the document real quick. These documents, released by the International Astronomical Union...
Okay.
Resolutions B5 and Resolution B6 from 2006. Resolution B5 defines a planet as a celestial body that A, is orbiting the sun,
okay,
B, has sufficient mass for its self-gravity to overcome rigid body forces, which just means it's heavy enough to be mostly spherical,
okay,
and C, has cleared the neighborhood around its orbit. Now, what I mean by cleared the neighborhood, it is gravitationally dominant in its own orbit,
okay,
so that there are no other bodies of comparable size other than its natural satellites, right? It's its own moons,
okay,
that would otherwise act to gravitationally influence that object. Mm-hmm. So, right, like there's nothing else in Earth's orbit besides our moon that is going to really affect our orbit around the sun.
Versus like the Kuiper Belt or something like that, which is full of other things.
Right.
Right.
The resolution also defines a dwarf planet, then, as a celestial body that is in orbit around the sun, like a planet, has sufficient mass to effectively become mostly spherical, like a planet, but has not cleared the neighborhood around its orbit.
Okay.
And is not a satellite itself. So, like, our moon is large enough that it would be considered a dwarf planet if it was not our moon. The fact that it is a moon of a planet already disqualifies it from dwarf planet status. But Pluto, the fact that it has not cleared its neighborhood, it has not effectively...
either like absorbed or kicked out other bodies.
Yeah.
Yeah.
There's enough other large stuff near it that affects its orbit enough that they consider Pluto to be a dwarf planet in this way. And the third part of Resolution B5 is defining all other objects except for satellites. Again, when I say satellites, I'm often referring to moons of things. All other objects except satellites orbiting the sun shall be referred to collectively as, quote, small solar system bodies.
Okay.
The previous terminology for this was minor planet.
Okay.
So sometimes you'll still see asteroids, comets, and other things like that referred to as minor planets on some old websites, or sometimes people just haven't bothered to update their own terminology because that's what their database was designed B4. Then resolution B6 is basically just a tiny little addendum follow-up to resolution B5.
Nice.
It's
the Pluto of the resolution.
Yes. Because it is the whole resolution is literally just Pluto is a dwarf planet by the above definitions. And is recognized as the prototype of a new category of trans-Neptunian objects. But which, when I say trans-Neptunian object...
Outside of Neptune.
Yeah, literally anything beyond Neptune is a trans-Neptunian object. But yeah, so part of the resolution that made Pluto a dwarf planet, gave it that sad little demotion, redefined these other celestial bodies as small solar system bodies.
Okay.
Which I'm not going to be doing that tongue twister to myself too much more this episode. So let's start with, I guess, the meteorite, meteoroid thing.
Okay.
Because that's easy to start with off the bat.
It's like the space version of stalactites versus stalagmites.
Kind of, yeah.
And it's all because of Latin.
Yeah, for the most part. The disambiguation here is that a meteoroid is any small broken off chunk of either an asteroid or a comet, and there isn't a great size definition for meteoroid, but the term can apply to anything as small as microscopic dust and to anything as large as a small asteroid, maybe like a few meters in diameter.
Okay.
Like the size of a car or
6 or 9 feet round kind of a thing.
Like maybe the size of a minivan.
Okay.
And a meteor, then, is the word used to describe any rocky object, such as a meteoroid, which has entered Earth's atmosphere. So regardless of its size, a meteor is an asteroid, comet, or meteoroid that has entered Earth's atmosphere.
Okay.
Or the atmosphere of any planet, really.
Right.
Which means that all shooting stars are, by definition, meteors.
Got it.
Which makes sense considering we call them meteor showers.
Mm-hmm.
So if that helps to kind of stick it in your brain as when do we call which one what?
Right. So
meteor shower,
meteors can be different things.
Right.
But they only become a meteor once they've entered the atmosphere.
Right.
And then they're all that.
Yes.
Yeah.
Yes. And the shooting star is really just what it looks like when a meteor has entered the atmosphere and is burning up due to the friction that it experiences from the air.
Right.
Which also, reminder that air actually does have mass.
Yeah.
I know we tend to think of air as being nothing, like it's all around us and it's basically nothing to us. But if you move quickly enough, air drags on you. It slows you down.
Right.
So.
Well, it's like turbulence in an airplane.
Right.
Yeah.
Right. You have to actually exert some force to move through it.
Mm-hmm.
And when you're moving at the speeds that these things do, you're going to get a lot of friction from that air.
Right.
Which creates a lot of heat and compressive forces on impacting meteors. Now, once a meteor strikes the ground, once it actually hits the Earth or any planet, any surviving chunk of that object are meteorites.
Jeez.
Yes.
Do you think they could have found a different word than meteoroid for the first ones? Like, I feel like meteor and meteorite makes sense.
Yeah.
But like anything that comes off of an asteroid or a comet that don't necessarily ever enter an atmosphere, a different word maybe.
Yeah,
would have been useful.
I wasn't in that room to make a decision. And honestly, I don't know if they would have listened to me anyway, because I would want to get really persnickety about the definitions. But a lot of these definitions, like the definition of exactly what size a meteoroid is, being already very imprecise, incredibly frustrating.
Yeah.
So frustrating.
Yeah.
Like, what is a small asteroid versus a large meteoroid? I don't know. You just kind of feel it.
Are meteoroids classified as small solar bodies then too?
Yes.
Okay.
The small solar system bodies. Thank you for making me do that again.
You're welcome.
So let's talk about asteroids then. Asteroids are, generally speaking, relatively small, rocky bodies, which actually range in size quite a lot. But they're smaller than planets.
And smaller than dwarf planets then too, right?
Yes.
Cool.
Yes. Smaller than dwarf planets because generally an asteroid has not overcome its rigid body forces.
Hasn't become a perfect sphere or
right.
close to.
Or, yeah, an oblate spheroid. Yes. Hey, I'm going to be pedantic about this. I love space.
Really? I'm shocked.
They can be as small as only a couple of meters in diameter. Meanwhile, the largest asteroid in our solar system is a 329-mile or 530 kilometer in diameter rock named Vesta.
Nice.
Yes.
It's a vibe.
Oh, absolutely. And Vesta, I believe, if I remember correctly, is the Roman equivalent of the Greek Hestia, or at the very least, they're both goddesses of hearth and home.
Mm-hmm.
This particular asteroid, Vesta, is the second largest object in the asteroid belt.
Huh.
With the largest being the dwarf planet Ceres.
Right.
Yes.
Who we love. Okay, so just for reference for people too then, the asteroid belt is the belt that's between Mars and Jupiter.
Yes.
The Kuiper belt is out past Neptune by Pluto.
Yes.
A lot of the same things are in both of those, but they're in two very different sections of the solar system in relation to the sun.
Oh, yeah.
And us.
Yes. And I'll mention those again in a little bit.
Cool.
Yes. Ceres is actually 940 kilometers in diameter.
Huh.
So a little less than twice the size of Vesta.
Yeah.
But then Vesta is the second largest
Right.
in that region. An easy way to think of asteroids in terms of sizes, and again, asteroid, meteoroid for the smallest side of things. Anything smaller than about 1 meter or like 3 feet is probably going to completely burn up in the atmosphere. So these are usually what we think of as shooting stars. There's some leeway there. But when they get to be around 7 meters large, it becomes more likely that at least a small chunk may survive re-entry.
Okay.
So in that range of like 1 to 7, it becomes slightly increasingly more likely that something will survive. Maybe you'll get a small chunk of meteorite out of it.
So that's like what? 7 meters is about just over 20 feet. So that's like...
Yeah, it's like 23-ish feet.
So it's like, for reference for people, because I always have trouble with visualizing sizes beyond like a yardstick.
Yeah, that's fair.
It's like 2 stories of a building.
Yeah.
Yeah. So it's about as tall or as wide in one direction or whatever as a 2-story building.
Yes.
Yeah.
At that point, a small chunk may survive entry, but they're still likely to mostly burn up in the atmosphere, especially because at about 7 meters is when we start to see airbursts become very common. An airburst is just when the heat, pressure, and friction of atmospheric entry overcomes the structural stability of the meteor, and it effectively catastrophically fails, structurally speaking, and explodes.
Right.
And once you get to about 20-ish meters in size, which is like a large house, they start to pose a real threat, especially in localized areas.
Okay.
So for instance, do you remember, and I can't believe it was this long ago, but do you remember the Chelyabinsk meteor over Russia in 2013?
Oh, yeah.
Yeah.
That viral video that was like one of the first viral videos on a bunch of different social medias or whatever.
Yeah.
Yeah.
That meteor was estimated to be approximately 20 meters, which is like 66 feet in diameter. And according to NASA, it exploded at an airburst about 14 miles in the air, which doesn't sound very close.
But it was enough to like shatter windows, crush cars that were directly underneath. It was like actually damaging. I remember that. Yeah,
the explosion was about 440 kilotons in terms of like TNT equivalent, which reminder that the nuke that the U.S. dropped on Hiroshima at the end of World War II was only 15 kilotons. So this 20-meter, 66-foot-ish meteor had about 29 times the explosive yield of the first nuclear weapon dropped on a civilian population.
Yeah. And the only reason it was not as damaging as it could be is because it exploded 14 miles in the air.
Right.
Yeah.
Right.
Like if it had actually made impact, that would have been beyond devastating.
Oh, it would have been horrendous for the surrounding area. I mean, as it is, the shockwave shattered windows for 200 square miles.
Yeah, that's crazy.
And injured over 1,600 people. Most of those injuries were sustained as a result of blown out windows and other shattered glass.
Sure.
But yeah, terrifying.
Mm-hmm.
This event actually was heralded as kind of a wake-up call to the international community regarding, hey, we don't really have much of a effective plan in place to deal with the possibility of impact events.
And it's almost like impact events have in the past been world changing.
Right.
Maybe we should think about this.
I mean,
Maybe we don't want to go how the dinosaurs went.
no,
know.
maybe not. I mean, granted, impact events of that size tend to be extremely rare.
Of course.
But this event is credited with kind of lighting a fire under the ass of enough of the United Nations, which coincidentally, United Nations was that day having a meeting to discuss how to defend from potential impact events.
Oh my gosh, that's ironic.
Yeah. This did result in the approval of creating the
The
international...
universe was like, here's proof that you should.
Right. It's like, great timing. Here, we're just going to give you just a little taste. Okay, cool. And then they created the International Asteroid Warning Network, which is a way for various international and national organizations to communicate and collaborate towards detecting and assessing potential impact threats.
Okay.
Which brings me to discussing objects that are close enough to Earth to potentially be worth monitoring. These are generally anything within 1.3 astronomical units of Earth, which an astronomical unit is very frustratingly defined as... Actually, I think they altered the definition a few years ago, but more or less an astronomical unit is like the average distance between the Earth and the Sun.
Okay.
So 1.3 of that distance
Jeez.
is considered to be like our neighborhood,
Okay.
at least in terms of what objects we bother to monitor.
Okay.
And so these objects are considered near-Earth objects.
NEOs.
Yes, NEOs. It's an umbrella term for many objects, but like 99% of NEOs are asteroids. So sometimes I might call them NEAs for near-Earth asteroids instead. I'll try to make sure I'm using the right version when the situation calls for it, but if I don't, you'll probably catch me on it.
I'll probably.
Yeah.
You could just do NEOs since the umbrella term is correct for everything.
Yeah, I'll try to. Most of the time. Anywho, NASA's Center for Near-Earth Object Studies exists to discover and log as many NEOs as possible, specifically noting anything larger than 140 meters, which is over 460 feet in diameter, and anything larger than 1 kilometer, since those are two kind of big milestones in objects that are deemed to pose the most significant threats to life on Earth.
Okay.
For reference, anything larger than about 140 meters would be considered a massive localized disaster with untold loss of life, tidal waves, earthquakes, fairly large area of effect, devastating.
Right.
Anything larger than a kilometer would be a potentially global disaster.
Great.
By the time you get to 5 kilometers or more, you're talking about potentially extinction level events. The Chicxulub meteor, the meteor that wiped out the dinosaurs, or at least is often credited with wiping out the dinosaurs, in the Cretaceous Paleogene extinction event.
Down in the Yucatan.
Yes.
Yes.
66 million years ago. That meteor is estimated to have only been about 10 kilometers or 6 miles in diameter. And its impact crater on the edge of the Yucatan Peninsula, like the crater itself, is 200 kilometers in diameter.
Yeah, it's huge.
And like a kilometer deep.
Yeah.
Yeah.
It's underwater too.
Most of it.
Yeah.
Yeah. Some of it is, like some of the ridge is on land in Yucatan itself.
Yeah.
Which is great for studying purposes.
For sure.
You don't have to get an asteroid that large for it to be incredibly devastating.
Right.
So.
Well, and they did, I can't remember what year it was, right? But they did those groups with NASA and the United Nations, whatever, that are part of this warning system. Didn't they do a big simulation with if a big NEO hit hit New York City or whatever, and how countries would have to react and what the damage levels would be and all that kind of stuff? It was I think one of their more recent important meetings of the last 5 years, maybe.
Yeah, I think they've had a few of those over the last few years. I do remember that if you go to NASA's website, there is an area where you can find a list of their simulations and activities they've done to try to prepare world leaders for this possibility.
Right.
I haven't looked through all of those, but I know there are several.
Mm-hmm.
So, yes. As of March 2013, which is like less than a month after the Chelyabinsk meteor, NASA's Center for Near-Earth Object Studies had at that time logged a total of about 9,700 NEOs,
Okay.
with just under 800 of them being greater than 1 kilometer, and about 5,500 of which were greater than 140 meters.
Okay.
So all of the others were smaller objects.
Right. Things we're not particularly concerned about.
Right. Where, some of them are still potentially quite concerning,
Right.
but they're not within those two categories.
Yeah.
They've been quite busy for the last 12 years. As of time of writing this episode, December 29th, 2024, they have logged a total of 37,160 NEOs, with 867 of those being greater than 1 kilometer and 11,157 being greater than 140 meters.
Yikes.
And the extra good news here
Uh-huh.
is that as of right now, there are no known objects of these sizes that are expected to impact Earth within the next 100 years. NEOs that pose any potential threat are studied in this way so that we can calculate and project their expected orbital paths so that we can hopefully figure out which ones to actually really keep a close eye on.
Right.
And so far, we seem to be all clear, but it's clearly of global interest that we keep monitoring.
Yep.
Just in case.
Yep.
So the efforts are forever ongoing to make sure that we didn't miss anything. Now, as for the location of most asteroids, and you mentioned this already, but most people have probably heard of the asteroid belt. It's a large, loose collection of asteroids occupying a range of similar orbits in between Mars and Jupiter.
Right.
And this belt is where the vast majority of asteroids in our solar system can be found. And it's estimated that between 1 and 2 million of these asteroids
Jeez.
are larger than a kilometer.
No.
With many millions more of much smaller asteroids.
Yikes.
The asteroid belt itself is about 1.5 astronomical units wide, which is 140 million miles or 225 million kilometers.
Okay.
So, again,
Large.
distances in space,
Hard to wrap your brains around.
yeah, it's already getting stretched a little bit.
Right.
There are also some asteroids known as Trojan asteroids, which I think are really weird and just fun and interesting. What?
I'm sorry.
What?
Oh, I simultaneously think of both the Trojan War,
Uh-huh.
obviously,
Uh-huh.
and condoms.
Yes. No, of course. I'm going to go out on a limb here and assume that the people naming these asteroids were thinking of the Trojan War.
Of course, because,
Right.
Everything in space has to be named after Rome or Greece.
Right.
Yeah.
Right. Trojan asteroids are asteroids which share an orbit with a planet, but are not satellites or moons of those planets.
Okay.
But they don't crash into those planets because they technically occupy these Lagrange points, L4 or L5, respectively, which really just means that those asteroids are at a point just far enough forward or far enough back, behind or in front of the planet to be stable in their position in the same orbit without crashing into the planet or leaving the orbit or
Right.
falling into the sun.
So they're like, are they typically further out than the moons,
Oh,
but on the same orbit?
Oh, yeah.
Okay.
Earth actually does have a Trojan asteroid,
Oh, do we?
at least one that we know of, which was discovered in 2011 after an infrared imaging study found the asteroid, which was named 2010 TK7.
Boring.
Yeah, I
Why do we
know.
get the boring named things? It's our Trojan asteroid. Name it something cool, like Helen or something.
Look, they'll Great Trojan War reference. Well done. It'll probably get an official name eventually.
Yeah.
But for now, it just has its, official preliminary designation.
Sure. It's data name.
Yeah, exactly. 2010 TK7 is only about 100 meters or 300 feet in diameter.
Okay.
and is orbiting the sun near Earth's L4 Lagrange point, which just means that it's about 50 million miles or 80 million kilometers in front of the Earth. Most Trojan asteroids, though, are Jupiter Trojans.
Yeah, that's not surprising.
Right, because...
It's by the asteroid belt and it's fucking ginormous.
Right. Jupiter's gravity is insane.
Yeah.
And it's really easy for Jupiter to, like, just kind of pull something off of the asteroid belt.
Yeah.
Now it's playing follow the leader. What do you know? And we can talk more about Lagrange points later if you want to. But for now, yeah, it's a point near or in the orbit of a planet that is a stable location for something else to also exist.
Right. Without orbiting the planet itself.
Right. Without being a moon. Asteroids can also be classified by their composition.
Okay. So not just size.
Right. Not just size and location and like motion or path, but by composition, like what they're physically made of. And there are 3 main types or like general categories of asteroids.
Okay.
According to NASA, the C-type or chondrite asteroids are the most common. They're probably mostly clay and other silicate rocks and are dark in appearance.
Okay.
The S-types are stony asteroids. They're made up of mostly silicate materials, but have some nickel iron throughout.
Makes it a little bit heavier.
Right. And then there are the M-type, or metallic, asteroids, which are mostly nickel iron with some other metallic traces, and probably some silicate present.
Are they shiny?
They do tend to be shiny.
Nice.
And these can vary in their composition a little bit, like from one M-type to another. They can vary in their appearance and composition depending on how close they were to the sun when they formed.
Okay.
So the ones that were really close to the sun probably experienced a lot more high temperature early on in their formation. And so the iron probably sunk to the center with a nickel kind of staying closer to the surface.
Okay.
And may even have formed some basalt rock on its outer crust because of that volcanic activity of just being extremely hot.
Right.
But at this point are cooled down and just rock.
Yeah.
But really cool to look at. Now, how asteroids officially get their names is also kind of weird because the International Astronomical Union is kind of loosey-goosey about it.
Of course they are.
Yeah. There's an asteroid named Spock, of course. But technically, it's not named for the Leonard Nimoy character from Star Trek. It's named after a cat.
Who's named after the Leonard Nimoy character from Star Trek.
Most probably, yes.
Great. Cool.
But many sources online will be very adamant in telling you it's not named after Mr. Spock. It's named after a cat, somebody's pet, which the International Astronomical Union does generally discourage naming asteroids after pets. So there's not that many of them named that way. And I think Spock might just be a holdover from before the International Astronomical Union really
had that kind of stuff in place.
Right. Or they might have allowed that one through and then went, wait, I'm sorry, did you say your cat? Well, shit, we already signed the paperwork. Moving forward, asteroid number 55555 is officially named DNA.
Great.
Asteroid 274020 is Skywalker.
Good. There has to be.
Of course.
I think when they run out of Greek and Roman things, they should just completely switch over to Star Trek and Star Wars for naming purposes.
Oh, well, like they've already kind of started doing that for a couple of these. Asteroid 1143, of course, Odysseus.
Lovely.
Yes. And asteroid 178008 is Picard.
Love it. I love that so much.
Yes. In our episode notes on our website, if we can, I would love to link the Minor Planet Center's database of asteroid names.
Yeah, I think so.
Just because I think it's really fun to like scroll through the thousands and thousands of names of these weird things and just go, that's a weird, funky little name.
So when are they going to get around to naming all of the planets they found outside of our solar system? Fun things.
Eventually, trademark. Someday. How about someday?
Great.
Yeah. The very near distant future date of
someday.
That time nebulously in the future. They're working around to it. They got a lot of data to work through.
Yeah. But they have enough time to make documentaries about these things and not have fun names for them.
Well, All right. Well, you need documentaries to drum up interest and keep people excited about it and keep coming so that they can spend more time naming them. Yes, but like, I get it. I'm not going to fault them for it. They'll get around to it. So let's get around to comets.
Okay.
So if asteroids are rocks flying around the solar system, comets are basically giant snowballs.
Cool.
In fact, the term dirty snowball has been used to describe comets for decades and actually originates from a 1950 theory of comets proposed by American astronomer Fred Whipple. Mm. Yeah, great name.
He's fun.
Yes. Comets are basically just big agglomerations of ice, rock, and dust all packed together. So, yeah, dirty snowball makes sense.
It's accurate.
Yeah. If you pack a pebble into a snowball, that's playing dirty.
Or dirt.
Right. They tend to have very large orbits, and the ones that the general public usually takes note of are the most visible ones that make themselves very noticeable when they pass into the inner solar system and pass close enough to the sun to heat up the frozen gases.
Right.
Those frozen gases at the surface of the comet then sublimate directly from solid to gas. Mm-hmm. And that gas then becomes the comet's tail, or at least the more visible tail of the comet. Trailing behind it and appearing to glow, the gas often ionizes, which in layman's terms, it's plasma.
Right.
It's actually like fire. It's just not a combustion reaction. And what's more fascinating to me about this is that tail of ionized gas is actually separate from the tail of dust and debris that gets left behind. Right? So as that ice sublimates, there's a lot of dust and pebbles that were packed under the ice that, well, now that ice has evaporated, it's gone. So it just kind of falls off or might break off as a piece of ice flakes off.
Yeah.
And then as that ice, those pebbles and dust kind of trail off behind it directly in the path of the comet, like the direction it came from.
Right.
Whereas the ionized gas tail is always pointing away from the direction of the sun.
Oh, interesting.
So the direction of the ionized gas tail changes relative to the comet's position around the sun.
Uh-huh.
And again, it has to be close enough to the sun for it to actually start melting.
Doing that process, right?
Yeah. The plasma tail can actually extend for millions of miles, which is especially impressive considering comets generally are pretty small compared to asteroids. Usually only a few kilometers or maybe a few tens of kilometers in diameter.
Asteroids can get ginormous,
right? We have asteroids a couple 100 kilometers. Now, where asteroids have the asteroid belt, as you mentioned earlier, the Kuiper belt is where a lot of comets tend to sit.
Because it's cold out there.
Oh, yeah. Oh, yeah. Most comets, if they got trapped in the asteroid belt, they'd probably melt or break apart.
Yeah, they're probably not really there much.
Yeah. The Kuiper belt begins at the orbit of Neptune, which is about 30 astronomical units. So again, the distance between Earth and the sun is typically about 1.
Right.
So 30 times the distance between us and the sun is where Neptune is.
Right.
Which is where the Kuiper belt starts. And the Kuiper belt extends another 20 AU beyond that.
Jeez.
So
almost the distance of Neptune to the sun, beyond Neptune.
Right.
Yeah.
And likewise, it is full of untold millions, if not hundreds of millions, of comets and asteroids. Now, the Kuiper belt was
other bodies we have yet to fully discover.
Yes.
Yes. We're doing a lot of study right now on the Kuiper belt and the objects out there.
Oh, yeah. But it takes time. Yep. There's a lot of data to sift through.
And it's really far away.
Yes. And this is like still just within our own neighborhood, basically. Yeah. Galactically speaking, we haven't even left the block.
Right.
Haven't left the cul-de-sac. No. The Kuiper belt was first theorized in 1951 by Gerard Kuiper, hence Kuiper belt.
Yep.
And it was theorized to be the home of short-period comets, sometimes also called periodic comets.
Okay.
Which are comets whose orbits take less than 200 years.
To get around the sun?
Yep. So if a comet has an orbit of 200 years or less, That's a short period comet. So Halley's Comet, which shows up in the night sky every 75 to 77-ish years.
Right.
That's a short period comet.
Mm-hmm.
However, the Kuiper Belt was originally theorized as an explanation for the short period comets because they couldn't account for those short period comets in their models at the time.
Mm-hmm.
Because they had already theorized the existence of the Oort cloud, which we do now also know exists.
Right.
But the Oort cloud was deemed too far away to explain these much shorter orbit comets.
Right.
Right. The Oort cloud is the point of origin for long period comets, which take longer.
Very, very far.
Oh, it's so far away.
And yet, it's still our block.
Yes.
Yep.
Yes. It's still our
sun.
block. It's not even like our neighborhood.
Right.
That's our block.
Yeah.
The Oort cloud is designated as a region in space between 5,000 astronomical units away
Jeez.
to 100,000 astronomical units away.
That's, yeah.
Yeah, no, we've absolutely entered the realm of distances that are not even remotely conceivable to the human mind.
Right.
Right. The Oort cloud is so far out and so large that many billions, with a B, billions of comets are estimated to inhabit this region. And being so far out, some long period comets have orbits that last thousands of years.
Jeez.
And when I say long period comet, I am specifically referring to comets that actually do sometimes enter the inner solar system.
Right.
And are visible as comets in that way.
Right.
The comets that just kind of stay in the Oort cloud full time, they can have orbits up to 30 million years.
Wow.
Yep. So 30 million years to orbit the sun once.
Yeah. Well, and here's the thing too, just as a, I don't know, clarifying thought. A lot of times these smaller bodies, asteroids and comets, their orbits can be very weirdly shaped. They're not, you know, even our orbit of the sun is not perfectly spherical, but it's a hell of a lot more close to circular than things like comets and asteroids can be because they're so small and other planets affect that orbit as well. So some of them can have like really skinny oval ones. And at one end of that really skinny oval, they're really close to the sun. And so that's when we see them in the inner solar system versus some that have these incredibly wide orbits that never even touch coming close to planets anywhere in our solar system.
Yeah.
So just as a trying to visualize how short versus long versus ones that stay in the Oort cloud, how that can happen.
Yeah.
It is through that kind of weird orbit shape process.
Yes. Not just the size of the orbit, but also the shape of it.
Yeah.
Yeah. Comets are wild.
Yeah.
They have to have spent enough time away from the sun to have accumulated all that ice.
Right.
Because if they just spent all their time right next to the sun, they're going to burn up immediately.
Exactly. Yeah.
Most comets don't get very close to the sun. For instance, Halley's Comet only gets, at closest, 55 million miles from the sun, which is pretty close. But any comets that do get much closer than that would typically be considered sun grazers.
Nice.
Which, side note, sun grazers sounds like a crazy like sports team name or something.
Yeah.
Those comets get close enough to the sun.
It's what we should name a type of spaceship when they...
Oh, yeah.
Yeah.
That's a great name for like a solar sailor spaceship.
Yeah.
Anywho, sun grazers are comets that get close enough to the sun to evaporate almost completely and or break up into meteoroids.
Okay.
I will say
that binding factor is no longer there
right.
of the ice. Yeah.
Right. I will also say it's not uncommon for comets to have orbits that are significantly more lopsided or like at weird angles compared to most of the solar system. So what I mean by that is that most of the solar system, like the planets and the asteroid belt, and even some of the Kuiper belt, can kind of be thought of as like a flat disk, more or less.
Sure. Like
pieces of pepperoni on a spinning pizza.
Yeah.
Right? It's like just different distances from the center or the sun. Comets are a not too uncommon exception to this, where they can orbit at weird angles. So let's see, an easy way to visualize this, and this might be a really weird visualization, but if most if most other objects in the solar system would orbit your head, if your head was the sun, right? Most things would orbit going like around your right ear, in front of your right eye, in front of your left eye, then behind your left ear, and make that orbit again and again, just at different distances.
Right.
Comets are not unlikely to come in from a weird angle above your head, down across your face, like past in front of the bridge of your nose, under like the left side of your chin, and then back behind and come up above and behind your right ear.
Yeah.
Kind of at like a skewed, tilted angle.
Sure.
Right. And I promise this will be relevant in a minute. It's not just a random fun fact. It will be relevant in a minute. Now, how comets typically get their names. Comet naming is frustratingly complicated sometimes because it's gone through multiple iterations.
Oh, good.
So the simplest way a comet gets their name is just the year it was first spotted. Right?
Yeah.
Like the Great Comet of 1680. But nowadays, comets are generally named for their discoverer. So, such as Halley's Comet. This applies whether the discoverer is a person or a spacecraft.
Okay.
But the International Astronomical Union only made that official and started enforcing that within the last century.
Oh, jeez.
So people have been doing it for longer than that, but it's only been official for about 100 years or less. A lot of recently discovered comets are therefore at least partly named for whichever observatory or satellite discovered the comet, since observatories and imaging satellites are really effective at detecting comets.
Sure.
Which means that a ton of comets have linear, SOHO, or WISE somewhere in the name.
Yep.
Those are all acronyms meaning linear is Lincoln Near-Earth Asteroid Research Project. SOHO is Solar and Heliospheric Observatory. And WISE is...
Because they couldn't just call it SHOW.
No. It couldn't be SHOW.
No, it had to be SOHO.
Right, because why not? And WISE is a NASA program. It's the Wide Field Infrared Survey Explorer. I'll also say that comets and asteroids both get provisional designations, which I kind of mentioned with asteroids earlier. But those provisional designations are often chosen long before they get an actual official name, like common name. And it can get kind of weird and complicated sometimes. We can talk about that more later if you want, because I think it's really cool. It's just, it gets really persnickety. So I'm going to leave that for later at best.
Yeah.
Yeah, I think that's all we got for comets at this point. Okay.
Cool.
Welcome to our low-gravity intermission in geosynchronous orbit around today's episode. While your eyes adjust to the dark of the night sky, please consider giving the podcast a rate and review on Spotify and Apple Podcasts, where you can also follow the show to stay up to date and never miss an episode.
If you'd like to join our email list, visit our website at www.hyperfixation-investigations.com and fill out the subscribe form on our Contact Us page. We greatly appreciate those of you already subscribed to our Patreon and are looking forward to making some merch and Discord content available in the new year of 2025.
2025? Why would you remind me? I still haven't gotten used to writing 2024 as the date yet. Speaking of, we should probably fly back into the time-relevant meteor shower topic at hand. All right, so let's finally actually get to talking about meteor showers. So if a meteor is what we call a meteoroid entering Earth's atmosphere, a meteor shower is just what we call many meteoroids entering Earth's atmosphere at more or less the same time. So why do meteor showers happen? Usually the answer is comets.
Okay.
One of the two tails of comets that I mentioned earlier, right, is that like trail of debris that breaks off of them as their ice melts.
The rocks and stuff like that.
Yeah, the pebbles, mostly dust, sand. And since a lot of comets have those orbits at weird angles, sometimes they happen to pass by Earth's orbit at these weird angles and leave a little trail of debris behind them, which we then smack into as Earth completes its orbit. So really, most meteor showers are just the Earth running headfirst into the debris field of a comet.
Nice.
And it's just, oh, hey, there's a lot of things that are breaking up in the atmosphere, burning up, and we get to watch a little light show.
Yeah. That's cool.
Yeah. This also means that meteor showers are generally reliable annual events.
Huh.
Because regardless of how recently the comet was nearby, they have been leaving debris in this field, in this trail, for untold years, thousands. So most of them, there is some debris that we're going to run into every time we pass through that point.
Even if they haven't been by recently?
Yeah.
Yeah.
So again, some of these guys, they'll take hundreds of years, and every year we run into some of their debris. And that debris field, because it's locked into more or less the same spot, because its orbit is just following the orbit of the comet.
Right.
We encounter it at the same point in our orbit every year.
Interesting, yeah.
Which also means that the angle of the meteors is going to look approximately the same every year, or like the angle they're coming from.
Okay.
So since the meteoroids are traveling the same direction every time we encounter them, and we encounter them at the same point every year, so when looking at a meteor shower, the meteors will kind of look or will kind of appear as if they're coming at you. And will be like kind of shotgun spreading across the night sky. So some going down a little bit more, some going side a little bit more, some going up a little bit more. But the point of origin that they appear to have is how they are generally named.
Okay.
The Orionids meteor shower, which occurs annually in October, looks like it comes from the constellation of the Hunter Orion.
Okay.
And the Ursids shower appears to come from the constellation Ursa Minor, which
is the Little Dipper.
The Little Dipper, yes. And Ursa Minor literally means little bear.
Yes.
Although sometimes, because we have to have exceptions.
Of course.
Yes. Sometimes meteor showers are named after the nearest bright star instead of the nearest constellation. Sometimes it's just, well, they're closer.
Why be, consistent with anything?
What? Well, because you don't want to have repeats, right?
Sure.
And sometimes you get some at the same time that are like really close to each other. So an example of this are the Kappa Cygnids, which...
It's a sorority name.
I know, it's a sorority name. But it's a meteor shower named for the star Kappa Cygni, which is where the meteor shower appears to originate during its peak activity. And actually the Kappa Cygnids are a great example of a meteor shower lasting long enough that its point of origin appears to move.
Oh.
Because the Kappa Cygnids start in late June and last until early September.
So right through rush season.
Oh, Jesus. I hate that I accidentally chose the most sorority-sounding meteor shower name for this example.
Fun fact about Kara, I did rush my freshman year of college.
I forgot about that.
I forget about it too.
Anywho, lasting from June to September, the angle that the meteors appear to be traveling from does shift over time because, right, Earth is still moving.
Right, yeah.
We're still moving through our orbit.
Yeah.
The Kappa Cygnids just happen to have a pretty wide debris field for us to interact with. At the height of activity, it appears to come from around the same area as the star Kappa Cygni.
Sure.
Also, Kappa Cygnids, additionally weird and rare in that they're not an annual event. They're an exception to that. That meteor shower only happens more or less every 6 to 7 years.
Huh.
And they vary pretty wildly in how intense the meteor shower actually is. And if I remember correctly, that is largely just because of an inconsistent debris field. There's not a ton of it necessarily, well spread out.
It's more in clumps or something.
Yeah, so sometimes it's...
So we sometimes just kind of go through it where there's a little hole or a path or whatever, and other years we go right through one of the clumps and get a ton. Right,
to my understanding, at least. All right, so now let's actually get to the meteor shower that I mentioned way back at the beginning of this episode.
And why this episode's happening now.
Yes, don't look at the timestamp to see how far into the episode we got before I mentioned this again. The Quadrantids. The Quadrantids meteor shower is currently ongoing in the northern hemisphere. It's an annual meteor shower that begins in December and peaks in early January. So the peak of a meteor shower is the time during which the highest number of shooting stars are visible. And most meteor showers have a peak of up to 2 days.
Okay.
The Quadrantids have a very short peak.
Yeah, I was going to say, I feel Well, I mean, growing up in the Northern Hemisphere, our weather is usually kind of shit at this time of year.
Yeah.
So seeing the night sky at all is hard, but, I feel like I've never seen them.
Yeah, which, fair, because the Quadrantids' peak activity is only like 6 to 8 hours.
Jeez.
Yeah, so it's like one night. You really gotta get lucky,
Right.
get out there and see it, or, yeah, too bad.
Right.
Well, at least for the peak activity. Most people will likely miss that peak activity.
Yep.
The good news, though, is that this shower does last weeks. So, again, from December to January, the shower began on December 26th.
Nice. Boxing Day.
Yep. And it will run until about January 16th of this year.
Aw.
So the average
That's
number...
near my mom's birthday.
Yes.
Shout out to Suzanne. We won't tell everybody how old you're turning.
Shout out also to my grandfather, whose birthday was just the other day.
Oh, very nice.
Where was I? Right. The average number of shooting stars visible during like the full run of this meteor shower is about 25 shooting stars per hour.
Wow.
And according to NASA, the peak activity of this shower is typically about 120 shooting stars per hour, though numbers as low as 60 per hour and as high as 200 per hour have been previously documented.
Wow.
And I will say that even NASA on their website calls out this meteor shower as being considered one of the best annual showers. The shower should be most visible in the northeastern part of the sky in the northern hemisphere.
Okay.
So it's best viewed by those of us up here in the northern hemisphere, but it's not too uncommon for it to be at least somewhat visible for people in the southern hemisphere that are less than 50 degrees latitude away from the equator.
Huh.
For those of you listening on release day, the peak was actually yesterday, January 3rd, at around 6 p.m. GMT, or midday for those of us in Central Time, which means that for most Americans, the best time to see the shower at all was at dusk last night. If the sky was clear, which, good luck.
Right.
Though most of Europe would have likely had a better shot at viewing for the longest amount of time.
Because it's darker there at the time.
Right. Well, it's 6 p.m. GMT is...
Greenwich Mean Time.
Yes.
Right.
Yes.
Which is in Britain.
Yes.
Yeah.
So, thankfully, though, the moon shouldn't be much of a hindrance this time around.
No, because we just had a new moon.
Right. The moon is only about 11% full in a waxing crescent. So, the moon shouldn't be shining too brightly, which if it was... that could potentially obscure some of the less bright meteors.
Sure.
Although this meteor shower is also known for having a relatively high number of fireballs, which fireball meteors are when a larger meteor explodes. So it's a brighter, typically more visible and like longer lasting streak of meteor than the average meteor streaks that we think of as shooting stars.
Right.
And those fireball meteors still look like streaks. They don't really look like balls of fire because they're moving extremely quickly, and as they break up and experience their catastrophic disruption, as the pressure, heat, and friction break them apart, they still are traveling incredibly fast.
Right.
So it still will be a large streak in the sky. It's just there are a large number of more visible bright objects, typically. The Quadrantids actually earns their name from a constellation that we don't actually use anymore.
Interesting.
Constellation named Quadrantids Muralis.
Okay.
This was created by French astronomer Joseph Jerome Lefrançois de Lalande in 1795, and the Quadrantids meteor shower was first observed in 1825 by Antonio Brucolasi. And then again in 1839, two astronomers, Edward C. Herrick in Connecticut and Adolphe Quetelet in the Brussels Observatory in Belgium, both independently of each other observed the shower again and suggested that it was likely to be an annual shower.
Okay.
Now, the International Astronomical Union created an officially recognized list of constellations in 1922, which did not include Quadrantids Muralis.
Why?
They didn't want to.
Cool.
They did include its neighbors, Draco and Boötes. Therefore, since the apparent point of origin is kind of in the Bootes constellation, sometimes the Quadrantids get referred to as the Bootides.
Okay.
But I think the Quadrantids sounds better.
Yeah.
And technically, they never actually bothered to officially change the name of the meteor shower. So I'm going to keep calling it the Quadrantids because, again, officially that is still their name. And I'll make sure to put at least one image in the episode notes showing the Quadrans Murialis in relation to other nearby constellations.
Cool.
That constellation, by the way, was actually named after an astronomical device called a quadrant, which kind of looks like a less complicated sextant.
Okay.
The Quadrantids are also a rarity among meteor showers because the parent object of these meteoroids is actually an asteroid.
Not a comet.
Right.
Cool.
Now, this asteroid 2003 EH1, discovered in 2003 by astronomers as part of the Lowell Observatory Near-Earth Object Search Program at Anderson Mesa Station near Flagstaff, Arizona. Despite currently being an asteroid, it is generally believed to actually be an extinct comet, by which I mean it was a comet that has since burned away all of its ice.
Right.
But there is enough of a body left that it still has like a rocky main structure that is staying together.
And orbiting the sun.
Right. So this actually isn't too uncommon for some asteroids near us to be identified as potentially extinct comets.
Yeah.
So that is, I think, basically all I have on the Quadrantids and meteor showers in general.
Yeah.
But I do want to say that if you don't have time to go see the current meteor shower and or you actually want to get the chance to go see a night of peak activity, the next best meteor showers that I can suggest for you to go watch that have like really sharp peaks like this one are the Lyrids, Leonids, and Ursids. So get ready to mark your calendars. These meteor showers will have peaks at the following dates.
Okay.
April 22nd for the Lyrids.
Cool.
November 17th for the Leonids. And December 22nd for the Ursids.
Nice.
Though, of course, there are a ton of other meteor showers throughout the year. These are just the big ones that are like the most dramatic and have the largest peaks.
Right.
So I guess, unless you have anything else to add.
I don't.
Okay, then I guess I'll finish off with this. If you want to go watch a meteor shower, the two best pieces of advice I can give to you are this. Get away from the city, from any light pollution that you can. Go out into the sticks if possible, or, as near as you can get reasonably. And then just be patient. Especially if you aren't viewing a shower during its peak, and even if you are, it's going to take some time for your eyes to adjust to the dark, and there's going to be some lulls in activity throughout the night. So, if nothing else, have fun. I encourage you to go out stargazing sometime. Look up at the night sky once in a while and bask in the wonderful vastness of space.
Very nice.
I just think that's good fun.
Yes.
And deserves to be appreciated more.
That's a wrap on episode 8, Shooting Stars. If you'd like to delve further into this topic, our research sources and related images are posted on our website, hyperfixation-investigations.com. Again, that's hyperfixation-investigations.com. Thanks so much for listening.
Follow us on social media for updates and check out our Patreon to support us directly. Join our Discord community and receive other special perks.
See you next week, and remember, what's a little info dumping between friends?